Good day, ladies and gentlemen. This is our first discussion on physical sciences for grade 12's term 2. We start our discussion with an introduction to mechanics, work, and energy. The first thing to bear in mind when talking about work and energy is that at some point you will need to work with gravitational acceleration. For this, you of course know the abbreviation is G, and we always use 9.8 meters per second. Now, gravity is not constant across the planet, as you may or may not know, but unless you are specifically told otherwise, you always use 9.8 as your gravity. Now, if you were to think of the concept of work, the way that we define work in layman's terms, you might say something like washing the dishes is so much work. That is obviously very different from how we would define work in terms of physical science. For physical sciences, we define work as we have an object with a force acting on that object. So we have a force acting on the object. That force then causes movement of that object. And that movement of the object is going to be parallel to the direction of force. So if I were to put my pen down on my page and push it across the page to the left-hand side, I'm applying a force to the left. The pen is moving to the left. So in this example, work is being done. Now, this concept of the force being applied and the movement being parallel is integral to the understanding of work and energy. Please bear this in mind throughout our discussion for mechanics. Now, another way to perhaps look at this would be in terms of vector addition or subtraction. This is something that was done in grade 11 physical sciences. This sketch might seem familiar. What it basically says is that when we have an applied force, we have an x and we have a y component. Using trigonometry, we can break that applied force up into our x and our y component, with the formulas being Rx is equal to r cos theta and Ry r sine theta. So if you were to use this, let me just keep this close to hand, then we could say that work, the abbreviation being W, is equal to a force, because we need to have a force being applied. And we will then have a displacement, movement, and let's say x for this instance. And if we are talking about x, we of course use cos theta. So the way we calculate the work being done is we have our force, we have our horizontal displacement, and we then have the angle at which that displacement is happening. The example would be if you have a box and you are dragging that box. The force is being applied to the right hand side. The box is moving to the right hand side, so work is being done. But it is not perfectly parallel, so we need to take that into account as well. And that is where breaking the vector up into x and y components comes in. Now, work is measured in joules, the abbreviation of which being a capital J. Now, of course, force is always measured in Newton, and a displacement is always measured in meters. So should you in any example be given kilometers or millimeters or something, you need to always convert that to meters as well. Perhaps I shall W is equal to force delta X cos theta. That is going to be Newton. That is going to be meters. That, of course, is going to be an angle with your cos. And that is going to give you an answer in joules. Now, as I said previously, for there to be work, the object that the force is being applied on needs to be moving in the direction the force is being applied. So let us use an example of the box again. Let us say that you have a box. Of course, gravity is acting downwards on it, and you then lift that box onto your shoulder. So you have a force that is being applied to that box, and the box is on your shoulder, it's in equilibrium, your applied force is equal to gravity. Now you start moving. You are now walking. So you and the box, let's say, if you want to have a practical example, carrying a box of books to your car perhaps. Now, because you are moving in this diagram I've drawn to the right, the force you are applying to the box is going in an upwards direction. The movement is to the right. That means that our force being applied is not parallel to the movement. And that means that in this example we have here, you carrying a box on your shoulder, no work is being done. This is a trick that very often gets asked in exams and such, where this concept of force and the movement needing to be parallel is in essence the trick. So please bear this in mind. This is a very common example, very frequently asked. Now, we are nearing the end of our introduction for force and energy. There are just a few more things that we need to bear in mind. As I have stated already, we measure force or work in joules, and we use the absolute values or the magnitude of the force. So when we use this formula, we use the absolute values. The angle between the direction of motion and the relevant force vector, this theta, is measured from the displacement in an anti-clockwise direction. So we are going to measure from here anti-clockwise in that direction, because obviously it is this angle that we want to measure, because that's one we are going to use. Force, or work in this instance, is at a maximum when the force is exactly parallel. So what that means is if we have, let's use the example of a box again, and that box is being pulled exactly parallel to the surface, then the work being done is at a maximum. If we have the box on the surface, but it is being pulled at an angle, now we come back to resolving x and y components. So in this instance that we have up here, where the displacement and force direction is exactly parallel, we are going to have the maximum work being done. And the amount of work getting done gets smaller and smaller and smaller until you end up with your angle of force and your direction of displacement being at 90 degrees. in which case no work is being done, and that is of course the same as our previous example with you carrying a box on your shoulders. You also get something that is called a positive and a negative work. That will be the subject of our next discussion, so do not concern yourself over much on that. The only other thing that you need to bear in mind when we are talking about forces is that we can also determine the net work on an object when more than one force is acting on it by adding the scalar sums of the forces acting. And if more than one force is acting on an object, then we're going to use the net force for our calculations. So if we have, let's say, our box, and we have somebody pulling it from that side, and we have somebody pushing it from that side, we have more than one force being applied. So what we are going to do is we are going to add these forces to get a net force, and we are going to use our net force for our calculations. And the formula that we are going to use, obviously, work is equal to force delta x cos theta. That, ladies and gentlemen, is it for our introduction to force and mechanics. Our next subject of discussion is going to be the positive and negative work. Until then, have a good day.